Hello, Physics 20s. In today's lesson, we are going to start the fourth unit of study in Physics 20 on uniform circular motion and gravitation. And more specifically, we're going to, 1, describe uniform circular motion as a special case of two-dimensional motion. 2, explain qualitatively and quantitatively that the acceleration in uniform circular motion is directed toward the center of a circle. And 3, explain quantitatively the relationships among speed, frequency, period, and radius for circular motion. A good starting point for this unit would be to first identify what it means for an object to actually undergo uniform circular motion. However, to properly describe that, it's easiest to understand what uniform circular motion is if we talk about a physical quantity called period. We'll use the variable capital T to represent period. And period is the time required for an object to undergo one circular rotation or revolution. In the background of the PowerPoint, I have an image of a Ferris wheel. And in terms of what the period for a Ferris wheel would be, so say, for example, you got on at the bottom of the Ferris wheel, and then that Ferris wheel went around in a circle one time so that you're back to where you started from. The time required for you to go around in that circle one time is what we call the period. In terms of what it means for an object to undergo uniform circular motion, an object will undergo uniform circular motion if it travels in a circular path with a constant period. Now, I'm not totally sure what the period would be on the Ferris wheel. Depends on how fast the Ferris wheel is moving. But let's say, for example, that the period of revolution is 30 seconds. So if you get in at the bottom of the Ferris wheel, it takes 30 seconds for you to go completely around the circle. As long as that period does not change, then you're undergoing uniform circular motion. If, for example, in one revolution, the period was 30 seconds, and then in the next revolution, the Ferris wheel sped up, and then the period of revolution was only 20 seconds, then you would not be undergoing uniform circular motion. So it is necessary for us to have a constant period to undergo uniform circular motion. There's another physical quantity that relates to period. That's called frequency, and we'll use the variable lowercase f to represent this. Frequency is the number of cycles that occur in a particular unit of time. We are most familiar with frequency in Physics 20 when we think back to one of the labs we did using the spark timer. And in the spark timer, you needed to set the spark timer to either a frequency of 10 hertz or 60 hertz. 10 hertz means the spark timer makes 10 dots in 1 second. 60 hertz means the spark timer makes 60 dots in 1 second. So in the case of a spark timer, it would be the cycles would be the number of dots that's being made. In terms of circular motion, a complete cycle is how many times you go around the circle. So the frequency would be the number of times you go around the circle in a particular unit of time. As already mentioned, the most common unit of measurement for frequency is hertz. 1 hertz is 1 cycle per second. If you had 10 hertz, that would be 10 cycles per second. 60 hertz would be 60 cycles per second. In terms of uniform circular motion, though, I would expect the frequency to be a lot lower than 1 hertz. We'll look at an equation in a moment that I can use to determine the frequency. There is an inverse relationship between period and frequency. So if you look at the definitions for a moment, period is the amount of time for a cycle or time for a revolution. Frequency is just flipped around. Frequency is the number of revolutions or cycles per unit time. Therefore, they have an inverse relationship, and there is an equation on the formula sheet that shows this inverse relationship, and it looks like this. You have T is equal to 1 divided by F. Let's give it a quick example of this, just to talk about like what the frequency of this Ferris wheel might actually be. So I said, let's assume that the period, so capital T, is 30 seconds. That seems reasonable. 30 seconds for you to go around the Ferris wheel one time. If I take this equation and manipulate it for the frequency, it would just be frequency is equal to 1 divided by T, which would be 1 over 30 seconds. And then if I calculate the frequency, 1 divided by 30, 1 divided by 30 would be a pretty small number. So it gives you something around 0.033 hertz if I round this to two significant digits. So what that means is you would have 0.033 revolutions in 1 second. That shouldn't be surprising because it takes a long time for the Ferris wheel to go around the circle once. So because my period is so large and I have the inverse relationship between period and frequency, it means my frequency is going to be quite a bit smaller. Speed, which we will use the variable VC to represent. For the time being, the subscript attached to the V, we're just going to say it has something to do with circular motion. Circular motion is actually just a special case of linear motion. And again, we dealt exclusively with linear motion in the one-dimensional kinematics unit of study, and also the 2D kinematics unit of study when we broke things into an X and Y direction. Here's why it's a special case of linear motion. Let's say you have a can. Okay, I'll just shade the can in. This is like a cross-section of the can. And I'm going to draw a label around it. So I'll use purple to draw the label. So there should be like a label that's just on the outside of the can. Now imagine that like we made a cut here. Okay, we'll just cut the label at this point. And then what I'm going to do is I'm going to remove the label and unfold it. If I remove the label and unfold it, I could actually unfold it so that it is in a straight line. Therefore, if I went around the circle, if like I started at this X here and went around the circle one time, that'd be equivalent to starting at this end of the label and going to the other end. And again, since I'm going in a straight line, that's linear motion. So just kind of think of it like the reason that circular motion is a special case of linear motion is if you unfold the circle, you could unfold the circle into a straight line. For an object undergoing linear motion, specifically linear motion where the motion is uniform or moving at a constant speed or a constant velocity, we know that the speed of the object is equal to the distance covered by the object in a certain amount of time. What we're going to do is we're going to take that equation and we're going to derive an equation for the circular speed. So let's say that we are going to go around a circle just one revolution, so around the circle one time. And what I want to do is I want to identify what d would be in relation to the circle and what the time would be. Well, if I go around the circle one time, going around the circle one time is just the period of revolution. So the lowercase t, the time would just be the period of revolution. When you go around a circle one time, that is the circumference of the circle. There's different equations we can use to calculate the circumference. We have circumference as pi times the diameter, or since we know the diameter is just 2 times the radius, we also know that circumference is 2 pi times r. We're going to write it in terms of radius because most of our equations we deal with are in terms of radius and not diameter. So let's go to our linear motion equation. V is equal to d over t. And if I plug 2 pi r in for the distance, and I plug in capital T for the period, I would get an equation for my circular speed that looks like Vc. I have the magnitude of the velocity vector. Magnitude of the velocity vector is just the speed. We'll talk about the direction in a moment. Will be equal to the d is the circumference, which is 2 pi r, and the time is just the period of revolution. And that equation, just like the t equals 1 over f equation, is on the formula sheet for physics 20 and 30. One note, because the period is constant, again, so the assumption is we're undergoing uniform circular motion, and uniform circular motion, we have a constant period. So if our period is constant, and for a circle our radius is constant, what that means is as we go around the circle, your speed would also be constant. So that's another way we could define uniform circular motion, is that uniform circular motion is when an object moves in a circle with a constant period at a constant speed. Let's look at something a bit more complicated now. The velocity of the object going in circular motion. Velocity is a vector. Vectors have two parts to them. They have both magnitude and direction. So we already know from the previous slide that the magnitude of velocity is speed, and the magnitude of velocity, the speed, is constant for circular motion because the period and the radius are both constant. Direction is going to be a little bit more complicated. The example I'm going to use is, let's envision that I take a rubber stopper. This rubber stopper has a hole in it. I tie a string through it, and I'm going to take that string and I'm just going to spin it around in a circle. And I have a little animation. I don't know if I call it an animation, but a little semi-animation to show this. First things first, whenever I use this little crosshair symbol or this little plus symbol, this is an indication that is the center of the circle. What I have here is I have my rubber stopper. That's this rectangular block, and this purple line is going to represent the string. And what I want to do is I want to take this rubber stopper and I want to spin it around, and I want to spin it around in a clockwise circle. This red circle will just represent the trajectory of the rubber stopper. And if I go around clockwise, if I start on the left-hand side, sometime later, my rubber stopper would be at the top, then the right side, and then the bottom of the circle. In terms of the direction of an object undergoing circular motion, there's two components we need to look at to identify the direction correctly. One, the direction of an object in circular motion, in terms of my velocity, is always tangent to the circle at a specific location. And two, it depends on which direction you're rotating the object. Are you rotating in a clockwise circle or a counterclockwise circle? We've looked at what a tangent is back in the 1D kinematics unit of study. A tangent is some kind of graph or just some kind of function that you're plotting, is just a representation of the slope at that point. If we look at the left-hand side of this rubber stopper, and I said, okay, what is the representation of the slope at this one instant here? Well, the representation of the slope would just be a vertical line. The question is, does that vertical line point up or does that vertical line point down? The way I would answer that question is I would ask myself, okay, well, where is the object going to go in the next instant? If I start at the left-hand side of the circle and I'm going in a clockwise direction, for a brief instant, I need to be moving up. Therefore, if I draw the velocity of the object, so I have the velocity vector that's tangent to the circle. It represents the slope at that point, and it points towards the top of the page. If we go to the top of the circle, a tangent, which represents the slope of that point, would be a horizontal line. And because we're going clockwise, the direction would be horizontal slope and pointing towards the right. If I go to the right-hand side of the circle, the tangent would again be vertical slope at that point, and downward because of the clockwise rotation. And then finally, at the very bottom of the circle, our tangent would once again be horizontal, and since we're going clockwise, the vector would point towards the left. What this means is, just think about this. If you're twirling this rubber stopper, and let's say, for example, that I did cut the rubber stopper when it's moving around in a circle. So let's say, or cut the string. So let's say that the rubber stopper is at the very top of the circle, and I cut it just when it's at the top. What would happen is that when I cut it, this object would then actually fly out of the circle, and it would fly out of the circle in a direction that is tangent to the circle. Now, one thing about the velocity, so as we go around this circle, we know that our speed is constant. So for example, maybe we're twirling this thing around and maybe our speed is constant at like 20 meters per second, 20 meters per second, 20 meters per second, 20 meters per second. Even though the speed is a constant, because both the period of revolution and the radius is a constant, the velocity itself is not constant. So the velocity has two parts to it, the magnitude and direction. Magnitude's constant, your direction is not. At every instant that object is twirling around the circle, the slope is continuously changing. If the slope is continuously changing, then your tangent to the circle keeps changing, which means your direction of your velocity changes. If the direction of your velocity changes, it means my velocity is changing at every single point when an object is undergoing uniform circular motion. Final physical quantity we'll talk about in today's lesson is centripetal acceleration. This word centripetal means center seeking. So the century part of the word is center, the pedal part means we're seeking. The direction of an object undergoing uniform circular motion in terms of its centripetal acceleration is always going to be towards the center of the circle. If I go back to my diagram and I add an acceleration vector onto the diagram, if I look at the rubber stopper on the left-hand side of the circle, from the left-hand side of the circle, the center is towards the right, therefore your acceleration vector would point towards the right. Now, you got to be careful in how you interpret what acceleration is. So some people might say to me, well, wait a second, if the acceleration is towards the right, then why don't I just move directly towards the center of the circle? Well, acceleration doesn't tell you where you're going to go at a specific instant. It tells you how your velocity is going to change. So if I have velocity that's pointing up and my acceleration is towards the right, what this acceleration vector wants to do is it wants to change this velocity vector so it is eventually pointing towards the right. The thing is, it just takes time to do that. So let's go around in a circle and look how the acceleration and velocity would relate. What this acceleration vector would do, because it's always pointing towards the center of the circle, in fact, it's always going to be perpendicular, the acceleration vector, to your velocity vector. And what it'll do is it will continuously change the direction of your velocity, but it does not change the magnitude. Again, the magnitude of your velocity, your speed in uniform circular motion is a constant, but this acceleration vector is going to continuously change the velocity vector. So at this point here, my velocity is towards the top of the page. The acceleration vector wants to change my velocity, so I'm pointing towards the right. And when I get towards the top of the circle, it is towards the right. So at that point, the acceleration vector has done its job. It's changed the velocity vector from pointing up to pointing towards the right. The key thing here is that it just takes time for that to happen. Specifically, it takes one-fourth of a revolution or a quarter of a revolution for this change to occur. And if we go throughout the rest of the circle, we'll continuously observe this exact same change. So at the very top of the circle, the acceleration will be pointing towards the bottom of the page. So what this means is this acceleration vector wants to change my velocity vector, so it's pointing towards the bottom of the page. However, it takes a quarter of a revolution for that to happen. A quarter of a revolution later, well, that acceleration vector has done its job. The velocity vector on the right side of the circle is now pointing towards the bottom of the page. If we draw the acceleration vector, the centripetal acceleration at this point, it would now point towards the left-hand side of the page. So what this acceleration vector wants to do again is it wants to change the velocity of your object, so it's eventually pointing towards the left. And once again, it takes a quarter of a revolution for that to happen. Quarter of a revolution later, the velocity is pointing towards the left. And then to kind of get through one full revolution, at the bottom of the circle, my acceleration would then be pointing towards the top of the page, which means the acceleration vector wants to change the velocity of my object so it's pointing towards the top of the page. And as we can see, a quarter of a revolution later, we are doing that. So this is why it is necessary for the acceleration vector to always point towards the center of the circle. Because what it does is it constantly changes the direction of my velocity vector every quarter of a revolution. To calculate the magnitude of the centripetal acceleration, we have a couple of equations on the formula sheet, although the way it's presented is as a single equation. I'm not going to derive this equation. So we have the magnitude of my centripetal acceleration is equal to the speed of the object squared at whatever point you're looking at. Well, I shouldn't say whatever point you're looking at because the speed is a constant, divided by r. Because your radius of the circle is a constant and in uniform circular motion your speed is a constant, that means your magnitude of the centripetal acceleration is also going to be a constant. The direction keeps changing, which means the acceleration itself is constantly changing, but its magnitude is a constant. Now, if you take the equation for your circular speed and you plug it in, so that was that equation that looked like VC is equal to 2 pi r divided by t. And if I plug it into the equation and do some simplifying, I would then get your centripetal acceleration is also equal to 4 pi squared r divided by t squared. Both these equations together is the third equation for uniform circular motion. The first equation would be useful if you knew what the circular speed was. The second equation would be more useful if you knew what the period of revolution was. The second equation is probably more practical because it is a lot easier to measure how long it takes for an object to go around a circle compared to knowing, well, what speed is it moving at a certain point in the circle. So again, the first equation is good if you know the speed. The second equation is good if you know the period. Okay, so that's it for this lesson where we talked about what uniform circular motion is. We introduced two physical quantities, one being period, one being frequency. And then we talked about the magnitude and the direction of your velocity and acceleration of an object in uniform circular motion. And you can complete the assignment called uniform circular motion And I will talk to you next time where we start to get into the forces that are responsible for the motion.